Bismillah Rahman Rahim. Last time we have discussed dynamical system and plane given by x prime to be equal to a times x, where a is some 2 by 2 matrix and x is 2 by 1 column vector. And we discussed that so far we know that 0 0 is always its fixed point, and we have already seen in the last video that if one of the eigenvalue is less than 0 and other is greater than 0, then the behavior is typically what we call the saddle. In other words, the equilibrium point is saddle. So the 0 0 origin is saddle. And today we are going to consider the dynamical system, planar dynamical system of this form, x prime to be equal to a times x, and in this case we will consider a to be lambda 1 0 0 lambda 2, and assumptions on these lambda 1 and lambda 2 are lambda 1 is less than 0 and also lambda 2 is less than 0. But one more thing that I'll consider over here is lambda 2 minus lambda 1 is less than 0, sorry, greater than 0. Okay, so in other words, what does this mean? This means that lambda 2 and lambda 1 both are you know less than 0, but lambda 1 is less than 0, less than lambda 2. So that means that the magnitude of lambda 1 must be greater than magnitude of lambda 2, because the negative number, if a negative number is greater than another negative number, then the magnitude of the other negative number should be greater than to the similar one, like this minus 2 greater than minus 3. So its magnitude should be greater than minus 2, like that. Okay, so these are two crucial assumptions, and we will be following those. Or we can say that our system is x prime equal to lambda 1 x and y prime is lambda 2 x, that is x prime to be equal to lambda 1 0 0 lambda 2 x, with lambda 1 being less than lambda 2 being less than 0. This is the case, and we already know that you can solve on the same lines as we did in the previous video, and you can conclude that x1 of t, which is e to the lambda 1 times t, as this eigenvector 0 1, and we can have x2 of t with e to the lambda 2 t with 0 1. It's not hard to show. The computations are same as we did in the case of saddle. So the general solution would look like alpha times e to the lambda 1 t 1 0 plus beta times e to the lambda 2 t 0 1. Okay, so this is going to be the general solution, this one. Don't forget that lambda 1 is less than lambda 2 and both are negative. So one more thing that you can observe is as time goes to infinity, this quantity will also converge to 0 0. x1 will also be going to 0 0, and this will also be converging to 0 0 origin. Why? Because this lambda 1 and lambda 2 both are negative. So we know that this limit t goes to infinity of e to the lambda 1 t is also 0, and t goes to infinity e to the lambda 2 t, this is also 0. So that means that this x of t will ultimately be converging to 0 0, or origin. And we can conclude from here that every solution will approach to 0. I mean 0 0, this origin. The next question is, now this is my 0 0 origin. The question is, how will the trajectories be approaching on the phase portrait? How will the trajectories be approaching to this 0 0? So well, we can do this in multiple ways. One of the way could be, uh, we can do one thing. We can calculate the slope of the curves dy by dx, which can be dy by dt, and divide by dx by dt. So for this we need to have y of t and x of t. And from general solution, we can see that x of t is nothing but alpha times e to the lambda 1 t. So x prime would be lambda 1 times alpha e to the lambda 1 t. And you can also see from general solution that y of t is beta times e to the lambda 2 t. So y prime of t should be lambda 2 times beta times e to the lambda 2 t. I can substitute these values over here and I can get, and instead of dy by dt I can put this value lambda 2 times beta e to the lambda 2 t divide by lambda 1 alpha e to the lambda 1 t, or I can write lambda 2 by lambda 1, and in fact beta over alpha, and then e to the lambda 2 minus lambda 1 times t. Now you can realize that is lambda 2 minus lambda 1 is greater than 0 from our assumption. So for suitable values of beta and alpha, okay, beta should be not 0. If beta is 0, then this will go away. But for non-zero beta, as t will go to infinity, this quantity will also be going towards infinity. Why? Because this is positive. Okay, so as this will be going to infinity, then this number is either positive or negative. So as a result, as t goes to infinity, our dy by dx will be approaching to either plus infinity or minus infinity. And what does this mean? We know that uh, the lines or curves which are parallel to y-axis will have slope plus infinity or minus infinity. So this means that the trajectories will be approaching to 0 0 along this y-axis. Okay, so the trajectories will be approaching to 0 0 along y-axis. Okay, so in other words, I can show you that how the behavior will be there. That's my y. So this is our phase portrait. So the any other trajectories will be moving towards origin and tangentially to y-axis. Okay, so if there is any other trajectory, it will be moving tangentially to y-axis. It should be tangentially to y-axis this way. It's very crazy. So lines have to move towards origin tangentially to y-axis, like, and they will be directed inward towards origin. Okay, on the same lines from this side, the trajectories will be moving to 0 0 along tangentially along y-axis. Forgive me for my crazy drawing. I'm going to show you on phase portrait plotter as well to have a clear understanding. So on the same lines from this side, from the other side, trajectories will be moving towards origin and along the tangential direction with y-axis. So this way, tangentially to y-axis, like this way. And these trajectories are also directed towards origin. So you can realize that when we were starting our problem, lambda 1 was less than lambda 2. So lambda 2 was corresponding to this y-axis. So the trajectories will approach to origin along the eigenvector eigenvector of uh, greater eigenvalue, because this was greater eigenvalue, no, lambda 2. So and then magnitude lambda 1 was greater. So lambda 2 along lambda 2, y-axis was the direction of lambda 2, so the trajectories are approaching along lambda 2. We can consider one example. For example, I can consider this example, x of x prime to be, let's say, minus 2 0 0 minus 3 and x bar. Let's plot this on phase portrait plotter. So this is going to be minus 3y, this is x prime, this is y prime. So let's plot over here minus 2 times x, and then we have minus 3 times y. Okay, so the eigenvalue corresponding to x should be less than that of y. So let me put it as 5. Now the eigenvalue for y-axis would be greater than that of x-axis. Now let's plot this. So you can realize that the trajectories are, these are trajectories approaching to 0 0 along the y-axis, tangentially along y-axis. You can realize these trajectories. So this is the behavior, and this behavior, and so it was 5. So what is the takeaway message of this discussion? The takeaway message of this discussion is, if both lambda 1 and lambda 2 are less than 0 for this system, for this, then all trajectories approach to origin, and we call 0 0 as sync equilibrium point, and this point, this sync is also a stable point. So when the behavior is sync, you mean that origin is stable. When origin is sync, you can also call that this is stable. Okay, and what more? And the trajectories will be moving towards origin along lambda 2's eigenvector. What will be the, whatever will be the lambda, whatever will be the eigenvector corresponding to lambda 2, the trajectories will be moving to 0 0 along that particular direction. So let's meet in the next video with example related to this sync, another example.